Hello everyone, I'm Munira Raushan and presenting with me is Ahana Abrar. Today we will share our work on ejection fraction estimation from 2D echocardiography via left ventricular segmentation. We will explain why EF matters, how we designed our pipeline, what results we got, and why we think this approach can make a real clinical impact. Ejection fraction, or EF, is a vital measure of how well the heart pumps blood. Clinicians use it to diagnose and classify heart failure, and it guides treatment decisions. MRI provides the most accurate EF but is costly, slow, and not available in many hospitals. Echocardiography is the standard tool because it's fast, affordable, and widely accessible. The challenge is that manual EF estimation from echo images is time consuming and highly variable between observers. So, our aim is simple: develop a method that automates EF estimation in a way that is consistent, fast, and still interpretable for clinicians. Deep learning has already been applied to EF prediction. DPSNet reported a mean absolute error of 6.2% with correlation 0.87. On the other hand, EcoEFNet did slightly better with 5.9% error and correlation 0.89. Econet Dynamite, on the other hand, trained on a very large video set, achieved 4% error and correlation above 0.95. These are the strong results, but there are trade offs. Most of these models are complex, depend on massive datasets, or predict EF directly without showing intermediate steps like segmentation. On the CAMUS dataset, prior studies mostly reported segmentation dice scores, but did not check how segmentation accuracy translates its EF accuracy. That's the exact gap we address in this program. Our pipeline is designed to be transparent and interpretable. We use apical 2 and 4-chamber views at both end diastole and end systole. First, we segment the left ventricle. From these masks, we calculate end diastolic and end systolic volumes. Finally, we compute EF using the Simpson's biplane method. To study the effect of architecture choice, we tested 4 models: U-Net, ResU-Net, PLVSNet, and MAEFNet. Now Arnav will walk you through our dataset, training setup, and the results.
Thanks, Monira. Now let's move on to the dataset and training setup. We trained and evaluated our models on a CAMUS dataset, which contains 500 patients. The split was 400 for training, 50 for validation, and 50 for testing. Each patient has both 2CH and 4CH views annotated at ED and ES. We split it into 400 patients for training, 50 for validation, and 50 for testing. For training, we used the Adam optimizer with a learning rate of 0.001, batch size of 16, and trained for 40 epochs. Each model trained in about 40 minutes on an RTX 4090 GPU. At interface, the pipeline processed each frame in under 50 milliseconds, which makes it feasible for real-time use in a clinical setting. Here are the segmentation results. U-Net achieved the best validation dice score at 92.38%. ResU-Net was close behind at 91.69%, while PLVSNet and MAEFNet performed worse at 88.53% and 87.02%. So the classic U-Net, despite being the simplest, outperformed newer, more complex models. That's the important takeaway. Adding residuals or multiple attention modules didn't improve performance for CAMUS. UNET still stands strong as a baseline. Now, let's see how this translates into EF estimation. On the validation set, our method achieved a mean absolute error of 7.0% and correlation of 0.82. On the test set, the numbers were very similar, 7.3% error and correlation of 0.79. Bland Altman plot shows very small bias and limits the agreement within plus minus of 18%. This is clinically significant. EF error of approximately 7% are within the variability seen between two human experts, which is typically 5 to 10%. In other words, our system performs at the level of a second cardiologist. To further validate our approach, we analyzed EF, EDV, and ESB distributions across training, validation, and test splits. The distributions are consistent and realistic across splits. We also looked at EDV versus ESB scatter plots, which showed a clear linear trend. That makes sense. Psychologically, patients with larger diastolic volumes generally have larger systolic volumes. This check gave us confidence that our models' predictions are coherent and not just numbers. This slide shows quality segmentation overlays. On the left, for patient 75, the model segmentation matched the ground truth very closely, and EF was predicted accurately. On the right, for patient 286, there was a segmentation error near the mitral annulus, just at the base of the ventricles. That small error caused EF to be underestimated. These overlays are valuable because they show clinicians exactly where the model does well and where errors happen. That transparency builds trust in automated pipelines.
Let's discuss the findings. First, EF estimation error for about 7% is within the variability seen between two human experts, which ranges from 5 to 10%. This makes our pipeline clinically acceptable. Second, UNIT remains a strong baseline, even outperforming our more complex architectures. Third, compared with DPSNet and EcoEFNet, our results are competitive while remaining interpretable and lightweight. EcoNet Dynamic does better, but it requires large sign datasets and much more compute. Clinically, our method consistently distinguishes between reduced EF that is less than 40%, borderline EF that is in between 40 to 50%, and preserved EF which is more than 50%. These are the key thresholds doctors care about. In conclusion, this work presents the first systematic EF benchmarking study on the CAMUS dataset across multiple backbone architectures. Among the evaluated models, UNIT emerged as a top performer, achieving a DICE score exceeding 92% and an EF mean absolute error of approximately 7%. Importantly, these results lie within the variability observed among human experts, underscoring their clinical credibility. Unlike most prior CAMUS studies, we place particular emphasis on validating EF reliability through correlation analysis, bland Altman assessment, and clinically relevant cutoffs. The proposed pipeline is not only interpretable but also efficient, running in real time and offering tangible potential to support clinical decision making. Looking forward, our future directions include extending the framework to many other models, that is, to sign loops, validating its robustness across multiple centers, and investigating hybrid segmentation regression approaches. Thank you all for your attention.